So how about the previous week's question? Could you finish it? People who are in the call, were you able to do that? Yes, you finished it. That's great. So can you tell me the value? Well, the one which you got. Others? So should I assume that you have finished it, or you are wanting to do it in this session? See, either way is fine, okay, but communication should be made. So tell me, if you couldn't do it, we'll do it together in this class. Please respond, people. Without knowing your understanding level, how it becomes a bit difficult for proceeding further. So shall we proceed further, or shall we revisit the problem where we stopped in the last class? Okay, thanks for the response. I'll see. I don't remember what's the value. Okay, you're almost there. That's correct. Thanks, Arun. Thanks for your response. Okay, so only two of you have responded, right? So for the others, should I show the solution procedure, or you are sure that you will be able to solve it on your own? Will you be able to solve it on your own? Prince, can you just explain how did you solve? How did you come up with this 64? What approach did you do? And even Arun, you can also just comment. How did you get 64? I mean, you can just respond. What was your approach? Did you use design spec, or you just took pressures which we have calculated previously? There are two approaches, right? So the one which we discussed is just for initial guess. If we want to have an accurate answer, the best is to use a design spec available in Aspen, then use it, and then get an answer based on pressure we have calculated. Okay, this is an initial step. All right, so this will work in few cases, may not be in all. Okay, so so did you yeah, Mr. Arun, did you solve in a similar way, or you have used design spec? Okay, use the pure component analysis to get the pressure. Okay, that's a brilliant way. It's just for pure components, it will work all good. Which what essentially Prince have also done. So, but however, to generalize this, I'll just explain few more steps. Okay, in today's class. For others, I'm assuming that you are able to solve. Okay, if you don't communicate with me, it's my default assumption that everything is good with you and fine. So we'll proceed for today's class, and in between, I'll just go back to our Aspen question and discuss what are we supposed to do with design spec. I just want to start from basic questions, then come back to Aspen, because meanwhile others can join the session. Okay, fine. Anyways, so yes, coming to this week lectures. So professor basically, he discusses about different property analysis methods available in Aspen, and he discusses how to get a binary plot, ternary plot, different for different components and all. Basically, he was explaining through a few examples, and he also shown you what all the different types of data available in Aspen. Do a data regression? Is it possible to do it a data regression and get the binary interaction parameter out of it? So all those things were discussed, right? Model fittings, etc. Then yes, he discussed about residual plots. Briefly he introduced what is residual plot, and it's related to distillation and all. See, if you need any thermodynamic explanation at the back, please let us know. For example, in the during the last semester, people in the session, attending the class didn't know what is residual curve. Okay, so I took a special class on residual curves itself. This can also be done. Okay, so in case if you want to know the thermodynamics behind anything, it need not be residual curves. Okay, anything that can also, we can also incorporate those things into our sessions. Okay, but the only thing which you are supposed to do is inform me what you want me to teach. That will be a good way. This is an interactive session, right? So the more we have the interaction, the better the session becomes. Fine. So then later the professor discussed about data regression. He took some sample data available in NIST. Then he has shown you how do we calculate binary interaction parameter, right? Then yes, that's how this week lectures were designed. And fine, so I have very few questions. Okay, for today we'll go to the Aspen problem. So in the question which I'm asking, in the property environment, which among these is there under analysis thing? So I have four options. Okay, I'll show you in Aspen where do we have this property and where do we have this analysis block. But before that, I want you to answer this question. Okay, I have a poll for this. Just give me a second. Yeah, this was my first question. Could you finish the previous thing? I will just launch it later. Fine. So the question is over here. In the property environment, under analysis, which among these you will be able to do? This question has multiple answers, but choose one. That's fine. So out of 12, only 4 of you have responded. What about others? You don't know or you don't want to respond. Either way, right? Only 5? What about others? The question seems very silly, so that's why you don't want to answer this question, is it? Huh? Don't give your response, okay? It encourages me to discuss more and more if people start responding and asking me questions. Fine, anyways. So I'll just show you. So when you go to Aspen, see, this is your property table, right? So just a second. Yes. So the question asked is under the analysis tool. Okay, so under the properties, under analysis, what do we have? So just go to new and you'll be able to see that you have generic calculation, you have PT envelope, you can generate residual plots, you can also generate ternary diagrams. So all the 4 analysis can be done using the analysis option available under property in Aspen. Okay, so according to the question what has been asked, so the answer for the question will be 2, right? You are able to do a generic plot as well as PT envelope. If you see here, I've shown you we have generic and PT envelope. The other two which can be solved using this analysis tool is the residual plots and the ternary diagrams. Okay, the same thing is given over here. When you see on the right corner, top, you'll be able to see this pure component analysis, binary component, PT envelope, ternary diagram, residual curve. Is given as a shortcut over here, but essentially what runs in background is this analysis block. Okay, fine. Let me go to the next question. So when we are trying to develop a PT envelope, which among these may be specified? What are the basic input required for generating a PT envelope? I have a poll for this as well. Just give me a second. See, these questions are very simple to answer, but these are made to make sure that you are following the lectures. Okay, the basic idea of this MCQs is to know whether you are following the lectures or not. The later part comes to, once we have this information, The simulation part can be designed accordingly. Okay, so that's the basic idea of asking you the simple questions. Don't think that the session is made very easy. We require the students in the class will be over a range. Okay, so keeping those things in mind, we designed from bottom till the top end. Okay, so only 4 of you have responded out of 13. Let me see. 6. Thanks for your votes. And what happened to other 6? And I'm the 13th one, so what happened to other 5 in fact? Okay, no issues. So when we go to analysis, let us create a new PT. Okay, says PT envelope rate. Let us see what all it's asked for. So it is asking us for flow rate. Let us do a dummy run. Let's say we'll take nitrogen. It says what all the valid phases, right? So it is asking for vapor liquid, or it's asking for vapor liquid. So let us assume it's a pure component, so we'll say vapor liquid. And it's also asking for the method, based on which the calculations are supposed to be done. So the standard method which Aspen uses, there's the same thing which RefProp also uses. And then the second method is density. Basically it's density matching method. Okay, so density matching method will always be better than the previous one. Okay, so for your information, this density matching method is designed in our lab only. It's a product of ITM. So we know in and out of what is happening with density matching method and flash calculations which Aspen does. Okay, so this density matching method behaves far better than the existing conventional method, so preferably use that. So that's all. Those are the required inputs. It's asking for initial pressure and temperature just for calculation. So let's see what results it gave. Right, see, it's able to generate PT envelope. Essentially it calculates the saturation temperature at various pressures, or other way around, saturation pressures at various temperatures. It's you must have read about Antoine's equation, right? So this is Antoine's equation for nitrogen. Okay, it's the same thing which it plots. Okay, so with respect to this question, oh yeah, some more have joined. Okay, with respect to this question, the answers are the valid phases which we gave as vapor liquid, and the method which we chose density matching in this particular case, right? Then this is very simple question, let it be. Okay, now the question is, while performing binary analysis, which among these may be, you are able to choose what different kind of analysis in binary analysis. So I have 4 options. I'll just have a poll, then I'll wait for a few minutes. Yes. Okay, yeah, I'll explain PT in there. I'll finish this question and I'll explain PT in there. Okay. See, when you ask questions, I'll know what all the things which I need to explain. Okay, that becomes easier for me. So please make my life simple, yeah. Don't complicate it. So 5 odds. Where is that 6th person? Oh yeah, the 6th person is here. Anyone else? I got 2 more words this time. That's good. Okay, fine. Let us see. So now we are talking of doing a binary analysis, right? So when you go to binary, that's the question, right? It says binary analysis. So on the top you will be able to see this binary analysis. So it is asking us to give the input. So it says txy, it is able to generate txy, it says txy, txx. Okay, can you please comment what is difference between xy, xx and xxy? Anyone? What is the difference? What does xy mean? What does xx mean? What does xxy mean? Any response? Anyone on the chat box, please? Can you please respond? What do you mean by xx, xy, xxy? Do all of them mean same? Anyone, please? If you don't know, let me know that you don't know. I'll explain what it is. If you don't respond by default, I'm assuming that all of you are aware of it. Okay, x is liquid mole fraction. Thanks, Aaron. And why? Y is vapor phase. Okay, then what about the second x? We have two x's, right? X, x, y. See, when you go to this drop box, you'll be able to see that it's xxy, right? So what is this xxy? What is that second x? I think you perfectly made your guess. So when you have a liquid split, okay, so your basically you will have multiple liquid phases existing in the same mixture. In that case, you will be able to see it's a vapor liquid equilibrium. Okay, so now when you go to xxy, see it is asking for the second key component for liquid equilibrium. Okay, so essentially if you have only x and y, it's the equilibrium between one liquid phase and one vapor phase, that's all. When you have x and y, it's the equilibrium between two liquid phases and one vapor phase. Okay, so where do you see this phenomena? What all, can anyone point out some common examples? Where do you come across such thing? Liquid and vapor split. Which scenario do you see this in your practical life? Or you can also comment why it happens. You can comment on this question as well. Why do you have liquid split? Extraction distillation. Okay, fine, that's one example. Correct. Thanks for the response. Any other case where you see this VLLE? Basically you have liquid vapor all together in equilibrium. Or when does it occur? Azeotropes. Can you be more specific? What kind of azeotropes you're talking about? I don't know. Okay, fine. See, essentially, I was asking whether you're discussing about homogeneous azeotrope or heterogeneous azeotrope. Okay, that was my question. So, if you are talking of VLLE, then it's heterogeneous azeotrope. Okay, that was the word which I was expecting from it. Fine, no issues. Yes, extractive distillation, you will be able to see, you always introduce an entrainer to your system and then extract some of the required component and then you send it to a distillation. Yes, you in extractive distillation you have this, correct. And when it occurs is when you have similar components in the mixture and only one dissimilar component. For example, mixture of nitrogen and hydrocarbons will exhibit VLLE. Okay, so in this case, hydrocarbons means lower hydrocarbons, C1, C2, C3 and all. So if you have C1, C2, C3 in a mixture, if you add nitrogen to it, in for few temperatures, temperatures close to 100 Kelvin, pressure of 3 to 20 bar, they'll exhibit this VLLE. Okay, so basically it occurs when all the components in the system are of similar nature and you have only one component which is a foreign element. Okay, in this case we have C1, C2, C3 in a homologous, then we have an external component nitrogen to that, so this forms VLLE. Okay, even if you take a look at the examples which you study in your class, you will be able to see that you have only one component which is dissimilar and it forms then the system will form VLLE. Okay, just go back and look at your previous courses and observe, you'll be able to identify it. And yes, one student asked about a PTE curve, let me explain that. Let me do it again. This time I'll do it for a mixture. Okay, so I took this one and I want to generate PT envelope. Let me see. So I'll say my nitrogen flow rate is 0.79 and oxygen is 0.21. This is basically I'm generating for air, right? I'll say I'll use density matching method and let me generate. So it gives me some data. Let us plot this data. Okay, temperature and pressure. You see this? It's like an envelope, right? Just goes and comes back. So essentially it says that, oh, this is for a mixture, right? Now we'll do one thing, we'll take one pure component and compare our results with this. That will be a good comparison. I'll do only for nitrogen and I'll explain that. See, when we are plotting the nitrogen curve, you can see that at every temperature you have a unique pressure, right? Or vice versa. At one pressure you have a unique temperature which matches to this. However, when you see for the mixture, you can see that for every pressure you have two temperatures. Can anyone comment what are these, how these two are different? In one case we took nitrogen where we have only one unique temperature for every pressure, vice versa is also fine. However, in this case you can see that for every given pressure you have two temperatures and for every given temperature you have two pressures, right? So what is this two pressures different from two pressures where we are considering a mixture and we have a single pressure while we are discussing about only nitrogen. So what is the difference? What are these two temperatures or two pressures correspond to in case of a mixture? Any response? Anyone? Okay, that's great. That's the right answer. Thanks, Prince and Arun. So essentially, when we talk of mixture, it's the dew point and bubble point. Okay. In case of pure component, we don't discuss dew point and bubble point. It's saturation pressure, right? So now at any given pressure, we have two temperatures. The lower one will be its bubble point, the higher one will be its dew point. Okay. So if one is interested in learning this phase equilibrium and all, this will be very much useful. So Prince, do you want me to show you how to generate this, or you want me to explain what is PT envelope? What was your question? Essentially, for a mixture, you will be able to know how the system behaves at different things. So, okay, now in this case, can anyone point what is this one point over here where the pressure and temperature is the unique value, right? So, up till here, I have two values for everything, but at this location, it's 1 and 1. So, what is this particular point? Huh, that's great. Thanks. So it's the critical point, right? So at this curve, when you see, it will go. It's like an inverted parabola, right? So on one side you have liquid phase, on the other side you have vapor phase. When they come close together, it's called critical point. Okay. Okay, fine. So it's called critical point. Once you know at this critical point, you won't be able to distinguish between vapor phase and liquid phase, and there's a particular terminology used for the fluids which are operated above this pressure. It's called super fluid, right? Super liquid. So in this case, you won't be able to distinguish between liquid and vapor for super fluid cases. Okay. So that's all. This is the way we generate, and there's a lot of interpretation can be done from this. Okay, fine. Now we'll move on to the next question. That's all. It's very simple question. Yes. What options are available for selecting valid phases for generating ternary diagrams? Okay. Let me ask this question in the poll. This is live, is it? So this is one more question which is related to ternary diagrams. Okay, before going to ternary diagrams, where do you think these ternary diagrams are useful? What is the application? Extraction, okay. Any other? Is extraction the only application for this? Okay. Any other application? Let me see how many of you have answered this question. Only four. Okay. Five. Thank you. Seven. And I have to add one more person who gave answer in the chat. Okay, it's eight. To know whether azeotrope is formed or not. Okay. You know better than this from residual plots. You know a lot better. Okay, fine. Anyways, let me show you this ternary plot first example. Let me close all this. No, it's a ternary diagram, right? See, the moment you give this, it will give you the applications. You want to find azeotrope, you want to find the distillation. Okay, if you have any doubts related to thing where you don't have access for other material, you can just click on this help and see what all it does. Okay, see, it's ask about azeotropic analysis and go to ternary maps. It will talk about distillation synthesis, what should be done. So okay, let us do an example. For the components which we are selecting, I'm sure that there is no azeotrope. So what's this? Okay, we'll have to see the another example. I'm sure that for this particular case we don't have any azeotropes. Fine. So essentially you can use it for finding azeotropes as well. Okay. Okay. Yes. So could you finish it? I'm asking this question again. The previous question, let me launch it here. In the last assignment, we were discussing about VCRS cycle. So were you able to finish it or no? Shall I call from the beginning? It's not good, right? Okay, anyways, whether you have finished it or not, I'll explain it. See, the basic idea is we said we are using propane, right? So you know how to give component, all right? So we'll define one component, and the method which I have described in the problem is Peng-Robinson equation of state, right? That's the property method which we want to use. Then the first idea is go to simulation. Okay, set up the flow sheet. Okay, as an initial guess, we said that we'll take operating pressures from the PT envelope. Okay, but I'll show you a detailed analysis. Okay, we'll just construct this VCRS cycle which I have shown you in this question, right? It says compressor, then condenser, we have throttle valve, we have evaporator, right? These are the 4 unit operations we have. We started with compressor. The inlet to this is, we know that the evaporator comes out at 10 bar. The pressure is just initial guess, we just gave randomly. It's not, in fact it's not randomly given, it's a rational decision which we made based on the PT envelope. Then we said it's 1 kg per second. After giving this input, the discharge pressure is also rationally selected, which is 17.2 initial guess. Okay, yes. Then we said to the condenser outlet, it should be totally condensed, right? And that's why it is called as condenser. We'll say the pressure drop is 0, which is given in the question. Then we are saying the vapor fraction towards the end of the condenser is 0, right? That's the constraint which we gave. Then the total valve, the value we gave based on our rational decision, right? Then we said we have boiler. For boiler, we'll say the vapor fraction should be 1, right? Since it is entering to the suction side of the compressor. Suction side means the inlet of compressor, right? So here we have a physical tear. Basically the stream 1 and stream 5 are the same. Okay, we said this should enter the compressor, so it can never enter in two phase, it should always be in single phase. And after all, this is called evaporator, so it towards the end of the evaporator, the phase fraction or the vapor phase is expected to be 1. Okay, so that's the simple simulation. So before running this design spec, I'll just run this simulation. Okay, let me save, then run it. So the simulation runs good. However, we are not sure whether how far are we from the actual saturation pressure at 10 degrees, because we have roughly estimated the pressure. Now we would want to find out the actual pressure. So we'll go to design spec. Okay, we'll develop one design spec. Then what input we'll give is that we'll make sure that the dew point of stream 3, okay, say this is stream 3, right? We'll call it, the dew point of stream 3 is exactly 50 degrees. No? By varying what? Will vary pressure such that the dew point becomes 50 degrees. Let me I think I'm giving 15 bar. Okay, as an initial. Yes, I'll do it again for you. Just develop this new design spec. We'll say dew. It's a stream property, right? We are talking of dew point, right? It's the stream 3, dew point, temperature degree centigrade. We want to say T dew is exactly 50. Some tolerance. Then we want to vary the compressor outlet pressure, right? We'll say compressor pressure bar, let's say limits 10 to 20. So what we specified is vary the compressor outlet pressure such that the dew point of the stream 3 becomes 50 degrees. Okay, let's save this and run. Let's see what happens. So I have got some results. It says the pressure is 17.292. Now what we can do is we can just reconcile our results. So there's an option of reconciliation on the top right. When you click on it, all the results which we obtained will go as an input. So if you see the stream 1 condition, not stream 1, the compressor. So compressor condition, see previously we gave 15 bar, right? Now it is 17.02. So the results which we obtained in this analysis are given back to the system as an input. Now what we'll do is we'll deactivate this. For valve also, let me change the value. Okay. So the design spec for the second unit is also similarly done. We'll say the bubble point, right? And the bubble point of the stream 5 should be 10 degrees. That's what our target, right? We'll vary the valve outlet pressure. See, we selected block variable, valve, P outlet and bar, so on. So let me activate this, save this file, then run. See, I have results. Now it says that the actual value is 6.37. We'll just reconcile this. I have the results. Let me deactivate. Let me save this again. So now when you open the valve, you will be able to see, when you open the valve, you will be able to see that the pressure which you are supposed to operate the system is 6.36. Okay, so this is the generalized approach for this problem. Okay, so when you take pressure and temperature from PT curve, it's an approximate thing, but when you actually calculate it using design spec, it's proper way of doing. So this can be used instead in case where you have mixtures, okay, and need not be a pure component. So for the people who have reported the value of 64 kilowatt, it's correct, right? So that's what we got. Fine. So in this, do you have any question? Could all of you follow? Could you follow what I did? Yes, okay, that's great. Anyone else? Okay, thanks Arun. Okay, thank you. So I'm assuming others also could follow this. Should I assume so? That's great. Thanks for your replies. So that's how you're supposed to do this. Okay, I have some more questions. Yes. So here is your question. Residual curves, the composition trajectories of a binary mixture undergoing distillation and total reflex. Is it true or false? I think I have a poll for this. Let me just confirm. Just a second, Mr. Arun. I have a poll for this. Yes. So residual curves are calculated at the total reflex condition. Is it true or false? Yes, see, I have informed professor. Okay, in the last class you asked about assignment solutions, right? Uh, uh, I didn't get a response from him. Okay, I'll update you once I have it. Can we make a WhatsApp group? No, WhatsApp group cannot be made. Okay, when we see, once upon a time we had WhatsApp group, but all these phone numbers were misused. Okay, so then we decided that we won't have WhatsApp group for this online sessions. You'll have to manage, or just remember that every Tuesday you have this class, but sorry, WhatsApp groups can't be made. Okay, there were people who were misusing the phone number, so we don't want to get into the same thing again. In fact, last year I had great trouble in stopping people from making nonsense in class. They were playing some songs, showing there some videos, you know, using on unparliamentary language in the session. So it was becoming difficult with WhatsApp group and all. So we don't encourage it anymore. Okay, fine. Let me end this. So yes, when you generate residual curves, you can see that in one of the class, professor in fact mentioned that, saying these residual plots are the trajectories in the total reflex condition, right? Okay, fine. So yes, we have another question. Okay, so what is this NIST? What is NIST database? Before answering this question, what is NIST database? What does it include? Can you please comment? Or what all these databases? What does it contain? Any response? What data does this NIST people give us? Experiments of component. What experiments? When you say experiment, what is that experiment? Database processes different property data related to component and mixtures. Okay, what property data you're talking of? Can you be a bit more specific? Okay, that's one answer. Correct. Good. Thanks, Arun. Array, what thermodynamics? What in thermodynamics? See, thermodynamics is the ocean, right? So, what part of thermodynamics you're talking of? Distributes numerical database covering thermophysical property database as well as safety characteristics. Okay. See, essentially, NIST is not a big thing. This National Institute of Science and Technology. It's an institute name. They do a lot of experiments. Okay, they do a lot of experiments based on the VLE or VLLE measurements. Essentially, they'll take components, mixtures of various compositions. They'll see that at different pressures and temperatures, they'll calculate the phase fractions and the phase compositions. Okay, so just to discuss more, so how do I calculate the composition? Let's say I have a gas bottle with me, which is mixture of four components. Okay, just assume mixture of four components. How do I know the composition of the mixture? How will I know the composition of the mixture? Lab analysis. Okay, what is that lab analysis? What do you mean by that lab analysis? Chromatography. Okay, that's great. Any other means? If I don't even know what components I have, what experiment should I do? So my aim is to find what component is there in the mixture. Second aim is to find what is its composition. So I have two things to be done. So what all should I do for finding the mixture composition as well as finding the identifying the component itself? The one answer which you gave is absolutely correct. For knowing the composition, we do is, what we do is chromatography. Okay, in our lab we have gas chromatography. So we perform these experiments to identify the composition of the mixture which we are using our system. Okay, yes. And for identifying the component also we have one setup. If any one of you can respond, that will be great. Or if you have any idea, just you can just put some random experiment. It's called mass spectroscopy. Okay, so based on mass of the component, you'll be able to identify what component you have in the mixture. Okay, so basically this NIST people, they do a lot of experiments and they give. Okay, the other category is called cheme. They also have this, but it's not freely accessible. Okay, we need to pay for that. Okay, then yes. Yeah, I have another question. The data available with the NIST or DCAME, can it be regressed? That's the question I have. Let me just have a word. So the data available, can we do a regression using analysis tool? How I should stop expecting more than 5 6 votes? Yeah, 6. Okay, thanks. Fine. The available data in one of the session, professor had actually covered how do we model and all that. So with the available data from NIST or DCAME, we will be able to find the binary interaction parameter for the given component. Okay, we will be able to do that. Fine. So yeah, I think that's all I had planned for today. Do you have any things which you want me to discuss? You can just put it on the chat box. Do you have any specific topic which you want me to discuss? If it is a big topic, we can start a fresh lecture. We can start the topic in a fresh lecture or a residual curves. Okay. Any other thing? Any other topic? Anything is fine. Okay, it need not be directly related to Aspen. I can discuss the thermodynamics behind the Aspen. See, our lab essentially gives lot of code to Aspen. Okay, so we know what is the thermodynamics behind the Aspen. So I'll be able to explain that part as well. So you can ask in case if you need any help with respect to thermodynamics. One of the topic is residual curves. I'll take a special lecture on residual curves probably towards the end of this course. Okay, we'll cover these topics. One or two lectures I'll keep additional things for the topics which you suggest. Anything else? Aspen Plus problems for practicing. There is actually a book. Let me just see. Give me a few minutes. I'm just stopping the presentation.